Yeah. Okay. Yeah. Yeah.
Sorry, it's because of this metal thing.
Okay.
Ah, that's better, right?
Yeah. Yeah. Perfect. Thank you.
So sorted.
Extend screen. Extend display.
Wait, can I adjust it again a little bit? Otherwise, we wouldn't hear you. Ah, a little bit this one. Just stand one up. Yes,
Okay.
that's perfect.
Okay. Thanks.
Super. So you know that this is live stream when we
Yeah.
are
Yeah.
talking, and you're okay with
Yeah. It's fine.
it. Very good. Just double checking. Huh? I always try to avoid that.
Hmm.
Always say I don't want that because then I cannot say what I want to say. Oh, you also have to be political. Can you make statements about the gravitational wave detector community?
What kind of statement?
Exactly. Yeah. Atom interferometers versus laser based.
Oh, no comment.
The ask is unnecessary. Just when you do like that,
Uh
I
huh.
can cut the live feed.
Okay. Okay.
It's not recorded, so don't worry. Is it? What? Oh, already? Oh, but okay, very good. So we start. Uh, Thanks everyone for joining. Is the AC on full speed or is it? It looks so off. Is it? The fan on full speed. Thanks. So it's a pleasure. Ah, okay, good. Thanks. It's a pleasure to welcome TEJAS today.
Hmm.
He is finishing his grand Vienna tour,
Hmm.
so we are the last stop to basically see the whole Vienna quantum research landscape. Tejas is from Northwestern University. He's working there with Tim Kovaci on atom interferometry. They're also doing some really interesting axion search experiments, dark matter. So we will hear about that. Tejas did his PhD at Caltech, so he comes originally from condensed matter and then switched fields to work on atom interferometers, quantum matter, and search for new physics. Tejas, the stage is yours. We look forward to your talk.
Thank you. Well, thanks for the generous introduction, and I am happy to be here to share our most recent results on looking for ultralight dark matter using two optical cavities. So I'll start with a broad introduction to dark matter. So from the standard model of cosmology known as lambda CDM, we know that 25% of the universe consists of dark matter. Evidence for this comes from things like galaxy rotation curves all the way to the cosmic microwave background. And based on what we know so far from these probes is that the range of plausible dark matter masses spans almost 80 orders of magnitude. In this talk, I'll focus on this ultralight scalar field, which essentially acts like a classical cosine wave oscillating at the dark matter's Compton frequency FDM. This field phi is predicted to couple to the mass of the electron and the fine structure constant through these coupling constants in red. A consequence of this is that the Bohr radius, which depends on these two constants, also oscillates in response to the field phi, hence causing a change in the lengths or sizes of macroscopic solid objects like an optical cavity, which we can detect using optical interferometry. Now, even in the absence of a discovery, we can nonetheless set limits on these coupling constants. In this talk, I'll focus on this coupling constant because, as you can see from the symmetry of this equation, the limits that we infer for DME will also apply to DE as well. All right, so let's take a closer look at this field and better understand some of the ultralight dark matter physics. First is the fact that the amplitude of this oscillator depends on the square root of the local dark matter density. So let's take a look at its spatial distribution. As a reminder, our solar system moves around the galaxy like this, and our galaxy is engulfed in a spherical dark matter halo as such, and our detector located on Earth sees a dark matter wind like this. And from this plot, you can see that the local dark matter density on Earth is approximately 0.4 GeV per centimeter cubed. This is what is known as the standard halo model. There's another model which is a little less well known, which involves a relaxion star or a halo that's bound to the Earth gravitationally. This is an analogy to how the galactic halo is bound to the center of the galaxy. Now, this hypothesis is still consistent with observations as long as the radius and the density of this relaxion halo follows these two curves over here. Now, the reason to interpret our data in this particular model is the fact that the densities that we can get on the surface of the Earth can be almost 12 orders of magnitude greater. What that means is the field amplitude is boosted by 6 orders of magnitude, and hence the limit DME that we can get in this model is 6 orders of magnitude lower. So, having looked at the spatial distribution in these two different models, let's look at the conjugate variable, the velocity. So the velocity spread inside the halo is modeled by this Maxwell-Boltzmann distribution, whose center is given by the galactic, close to the galactic orbit speed, and its width is given by this so-called virial velocity. So this is for the standard halo model. In the relaxion case, this width is almost 2 orders of magnitude narrower. Now, this width is related to a statistical quantity known as the coherence time, given by this expression. And we need to invoke this statistical parameter because of the fact that our field itself is stochastic. Here's what that means. So in the first slide, when I told you that it acts like a simple cosine, that wasn't quite true because in reality, the amplitude phi naught and the phase theta are random variables drawn from these two distributions. So, and the coherence time implies that the Fourier transform is not just a delta function at FDM, but it's broadened by a certain amount. So what you end up doing is you have to sum over the Fourier components inside that broadened line shape, and for each Fourier component, you need to draw phi naught and theta from these distributions and perform a sum. And what the resultant time domain simulation of that looks like is as follows, where you have this cosine, which you can zoom in to see the actual oscillations at FDM, but the amplitude is oscillating. So the reason this is relevant is because when we interpret our data, we need to know whether or not we have performed sufficient averaging, because the field phi naught is the average of the field phi naught is related to the dark matter density, in this case the standard halo model, through this expression over here. But that's not true at all points in time. So the important thing to keep in mind is that as long as our detector is measuring dark matter over time scales significantly greater than tau c, only then can we use the average local dark matter density. And if it just so happens that your observing run is shorter, then you might need to deal with certain complexities associated with the fact that the field may not always be close to its average value, and hence avoid being fooled into setting a more optimistic limit than would actually be the case. Okay, so this is the basic physics of the ultralight scalar. Next, I want to talk about how would one go about probing such a field. So I'll make an analogy to visible matter. In the case of visible matter, you have a broad electromagnetic spectrum that is probed by different instruments, and they give you complementary information about the same object. In the case of dark matter, we have a very analogous situation where there's a broad spectrum that is being scanned by multiple instruments. Our detector falls in this particular category, where we look for an oscillation in the optical transition frequency inside an optical cavity or an atom. Now, the one challenge compared to electromagnetic telescopes, the one challenge here is the fact that the length scale of these experiments, which are typically tabletop, are much smaller than the wavelength of dark matter, which in our frequency range tends to be in the hundreds of kilometers range. So to put simply, if everything is changing, how do you know something is changing? Hence, you need to do this measurement in a differential way, which means that you either compare an atom to a cavity, two types of atoms, or two types of cavities, because assuming that the two things being compared are responding differently to dark matter. And this approach is necessary because there's not a way to shield dark matter that we know of. So in the next couple of slides, I'll just show you a few examples of experiments that are already existing in this category that we are going to compare our limits to put our work in context. So here are two examples where you have on the left a cesium atom and on the right an iodine molecule being compared to cavities. Over here we have cavity-cavity comparison. On the left you have LIGO, holometer, and GEO600, which are looking for oscillation of this beam splitter due to dark matter. It's worth noting that since the dark matter strain, in analogy to gravitational waves, is only influencing matter through the Bohr radius, the fact that LIGO has vacuum between their mirrors doesn't really help you, because we're looking for only matter changes. So these two arms are relatively insensitive. However, the oscillation of this beam splitter causes a slight asymmetry in this dark port, and that's how you would expect to detect a dark matter signal there. On the right, instead of two cavities, you just have a single cavity that is being monitored in a stroboscopic way. In other words, instead of comparing it to another cavity, it's comparing the cavity to itself, but a time-delayed version of itself through this optical fiber delay line. And finally, we have the torsion pendulum from a combination of etwash and microscope, where you're looking for an equivalence principle violation. And it's worth noting that in this case, they're agnostic to what phi represents. If you look at how phi couples to the standard model, there's two solutions. One is an oscillatory solution, which you already saw, and the second solution is a Yukawa type solution, and that's what the inverse square law tests probe, as phi being a mediator between standard model bodies, leading to a fifth force by ISL violation. While there are two different types of measurements, it's typically customary to put these limits on the same plot because they're still phenomenologically setting limits on the coupling constant. So here's a plot that summarizes all the experiments that I just showed you, and this thick dashed black curve is a projection showing how sensitive our detector could potentially be. Okay, so having given you some of the broad overview of the work being done in the ultralight scalar dark matter detection community, let me move on to the detection principle of our detector. So our detector is very analogous to LIGO, except, as I stated a few minutes ago, that one key difference is that instead of having a vacuum in between the two mirrors, we now have a solid object, or a spacer. In both cases, we can define a strain as the fractional length change, very much an analogy to the gravitational wave detector. However, there's a small caveat and an impediment to our detector, and that is that the two arms in the gravitational wave case are oscillating 180 degrees out of phase. That's due to the quadrupolar nature of gravitational waves. So when one arm stretches, one arm compresses, and at that point, you get a finite signal at the photodetector. But our field is scalar. What that means is the two arms are going to oscillate in phase, hence giving you a zero signal at the photodetector. So we need to find a way to ensure that the signal measured here does not vanish in the frequency range or mass range of dark matter that we care about. One of the ways of getting around this problem is to exploit the internal mechanical resonances of the cavities. So let's take a closer look at its mechanical properties. As a reminder, your cavity is going to respond to dark matter as such, and putting aside some of the complexities of finite element analysis, this very simple model captures the basic physics of what's going on, where you model the cavity as of length L, mass m, and spring constant k as a simple mass spring model. In the absence of dark matter, there's no oscillation, obviously, since there's no drive. However, when you turn on dark matter, you place this box inside an accelerated reference frame, and this bigger box now becomes your lab frame, where the box is being driven by dark matter with a form like this. And the mass sees a fictitious force and starts oscillating with an amplitude A and a phase theta relative to the drive. Now, if we define a mechanical transfer function H, which I will show in the next slide as well, as the displacement of the cavity in the lab frame divided by the dark matter amplitude, then doing some simple classical mechanics calculations, you'll arrive at this expression over here. And here's a plot showing you the amplitude and phase of this transfer function. In our experiment, for our sapphire cavities, we empirically measured the resonance frequency and the quality factor. Let's look at its behavior at different frequency regimes. So below the resonance frequency, you have the mass almost perfectly following the dark matter drive, and hence the transfer function is 1. But the more interesting regime is where you go past the mechanical resonance, where the mass almost completely opposes the displacement from dark matter. Hence, the transfer function is approximately 0, and the cavity recovers its original length. So in essence, even though I said we can't really shield against dark matter, it is effectively shielded against dark matter. So you can use a cavity that's in this range as your reference, and then measure the length of another cavity. for those, since dark matter is a big field, so it's not all people use cavities. So this is just a cavity 101, which most people here know, but I'll walk through it very quickly, where a cavity is an optomechanical sensor where we don't actually measure the length, we actually measure the frequency and infer the length from it. And because of this multiple reflections, you get a optical standing wave where, since the mode spacing is related to the length in such a way, we get such a relationship between fractional frequency change and the fractional length change. And this is a principle we exploit in detecting dark matter. All right, so as I alluded to a few minutes ago, we have two cavities. So let's look at the mode spectrum of those two cavities. Here's our apparatus where a common laser is resonant with both cavities, and then their beat node is being detected at this photodetector. Here's their mode spectrum over here, and the photodetector measures the frequency difference between these two closest modes. Here's a zoom in of what that looks like, where you can separate this difference into two components: a DC component, which corresponds to the mode spacing in the absence of dark matter, and this other component, delta F beat as a function of time, which models the oscillation of those modes because of dark matter oscillations. We can define a strain in terms of this second quantity, delta F beat, as follows, normalizing it by the optical frequency. And we call this the optical strain, is what we measure in the lab. And this optical strain is related to the dark matter strain, HDM, which is nothing but the fractional change in the electron mass in response to the field phi. And they're related by this detector response function A, which you probably already guessed has something to do with the mechanical transfer function. And it is indeed the case that A det is the coherent difference between the long cavity's mechanical transfer function and the short cavity's mechanical transfer function. They're color-coded for ease of visualization. So let's take a look at what A looks like as a function of frequency. First, you have the transfer function of your long cavity in red over here. The resonance frequency is determined by the length of the cavity, where Vs is the speed of sound in your material. In our case, it's sapphire. Now, the other cavity being shorter, its transfer function is given by this. And if I take a coherent difference, you get the dashed black curve over here. Now, note that in this middle region that's shaded and called the science band, your cavities are oscillating 180 degrees out of phase, kind of like the LIGO behavior we were aiming for. The other thing to keep in mind is the fact that both cavities are being driven by the same dark matter field, hence the coherent in the coherent difference function. That, in general, will not be the case for noise sources, which will be incoherent. So if the last couple of slides were a little bit technical, you can forget everything, all the equations, and just keep this very simple cartoon in mind. Here's the transfer function again. Here now I have plotted on a linear scale as opposed to the log scale from the previous slide, where the red and blue correspond to the amplitudes of the transfer function of the long and short cavity, and the dashed line is their difference. On the left side, since both transfer functions are 1, their difference is 0, and hence our detector has virtually no sensitivity in this range. In other words, the cavities are both oscillating together, and hence no net signal at the photodetector. On the right side, since both transfer functions are approximately 0, neither of them are responding to dark matter, and hence the sensitivity of our detector also vanishes. However, it's in this middle, quote-unquote, science band is where something interesting happens, where since you're past the resonance of the first cavity, your long cavity acts as a length reference, and then you're measuring the length oscillation of your short cavity, which is why you can intuitively see this having a high sensitivity in this particular window. So that's the detection principle of our detector. Next, I'll talk about the apparatus details. All right, so here's our apparatus where we have this breadboard shooting 2 laser beams into this cryostat where our 2 cavities are located side by side. Here's a top-down view schematic of this apparatus, and here's a section view viewed from here. Now, there's a lot of complexity in this diagram, and I'll walk you through what all the different components are in a minute. Each component, or each most important component, is serving an important purpose in enhancing our dark matter sensitivity. So I'll tell you what each of the component is doing by showing you a slideshow of how the sensitivity improves as we add one component at a time. All right, so here's a vanilla optical cavity system. Here's a section view where just 2 cavities sitting on an optical table, nothing fancy. This is the sensitivity that you would get, shown by the thick black curve in relationship to the other experiments that you saw previously. Now, at lower frequencies, denoted by this lightly shaded red region, you're limited by vibration noise. On the right, you're limited by laser frequency noise. Now, if I suppress laser frequency noise by, for example, adding a filter cavity at the top, then your sensitivity improves as denoted by the transition from this dashed to the solid curve over here. And now you're only limited, aside from vibrations, you're only now limited by 300K thermal noise and photon shot noise. Now, if I hang our cavities from a vibration isolation system and eliminate vibrational noise, we're only limited by 300K thermal noise and shot noise. Now, the obvious next step would be to make it cryogenic. And we do indeed see a massive improvement as shown here, where we took our nice vibration isolated system and put it inside a 4 Kelvin closed cycle cryostat. And now we're only limited by 4K thermal noise and photon shot noise. So hopefully I've convinced you that our apparatus, which took a lot of R&D to build, was the design was justified by our target dark matter sensitivity. Okay, so next I'd like to talk to you about the specifics of how these different noise sources influence us and what did we do to mitigate those noise sources. All right, so as a reminder, our 2 cavity setup is an optomechanical system where we're measuring the optical strain to infer the dark matter strain from here, and we need to be wary of this strain from noise sources. Noise can be of 2 types. One is length fluctuations caused by vibrations and thermal noise. The other one is frequency fluctuations from the intrinsic laser noise. I'll start with vibrations first. If you recall the simple mass spring model that I showed you a couple of slides back, where the system was being driven by a dark matter field, vibrations have a very similar effect. So they can essentially fool you into thinking that you're detecting dark matter even though you're not. One way to mitigate vibration noise, which is very standard in optical cavities in AMO labs, is to engineer the support points to minimize the impact of the vibrations. The second, which you already saw, is hanging our cavities from a multi-stage vibration isolation system. So let's take a closer look at this vibration isolation system. Here's a prototype of our vibration isolation system, which consists of 3 different stages. The first stage is an inverted pendulum consisting of these 3 legs, which can move at these flexures. On top of that is a geometric anti-spring filter, which consists of 3 blade springs meeting at a point over here. And from that point, you have a single wire pendulum from which your payload is suspended. And your payload is isolated from its environment through the properties of the pendulum. Here's a photo of this prototype. Here's a zoom in of the gas filter, gas being short for geometric anti-spring filter. And here's a zoom in of the flexure of the inverted pendulum. So the inverted pendulum offers you horizontal vibration isolation by tipping sideways with a typical transfer function that's given by this. It's the same is true for the single wire pendulum. and the geometric anti-spring filter offers you vertical vibration isolation with a transfer function typically in this range. Now, if you define a single stage of our pendulum as consisting of this geometric anti-spring and a single wire pendulum, then our payload's isolation from its environment is characterized by this transfer function, where you can see you can suppress vibrations by almost 3 orders of magnitude. Now, if you want to be a little bit greedy and get more isolation, you do something very straightforward, which is you stack them together. Here's a photo of our 3-stage vibration isolation system, and our final payload obviously consists of our optical cavities. Okay, so next on our list is thermal noise. Our cavities are composed of atoms, and these atoms are wiggling around due to thermal excitations. Going back to the mass spring model once again, you can think of the drive as random kicks from these atoms. Now, while I don't have time to go into the nuances of thermal noise, I will only cite the fluctuation dissipation theorem, which states that the strain that the cavities would experience from thermal noise scales as the root of the temperature, which is obvious given the name of the noise. But the other factor is the scaling as the inverse of the root of the quality factor, which is why we use high Q factor materials like sapphire, as well as crystalline mirror coatings that were developed by Crystalline Mirror Solutions, part of Thor Labs. Now, here's a photo of our vibration isolated cryostat with the schematic that you already saw on the left. Here's a zoom in of our 2 cavities side by side. One of the main technical challenges that we overcame in this particular apparatus is to achieve an optimal trade-off between vibration isolation and cooling power. And we did that with the use of these flexible aluminum thermal links. I'll show you one example as to why there's a tension between these 2 factors. So consider this example where you have a cavity sitting on this cradle, and this cradle is suspended from a top plate which has a high cooling power and is connected to your pulse tube or whatever cooling mechanism you have. Now your cooling power at the cavity is going to be determined by the thickness of this wire. The wider you make it, the lower temperatures you'd get. However, you'll also note that if you make it really big, it stops being a pendulum, and hence the vibration attenuation scales as the inverse of the wire diameter. So one way we got around this problem was to install these soft thermal links from the top plate to the bottom plate and from the cradle to the cavity itself. Here's a photo of that. And in this way, you still get the benefits of the pendulum while still getting a parallel extraction path over here. It's for this very reason that in addition to the cavities, these links are also installed at other points in the cryostat, as shown here. All right, so last on our list is laser frequency noise. Now, laser frequency noise mitigation is a very mature field with a wide range of tools at our disposal. In our case, the technique we used is pre-stabilization using Pound-Riever-Hall. And it works as follows, where we pre-stabilize our laser to an ultra-low expansion cavity before sending the picked-off beam to our science cavities. The way this helps us is that phase noise, intrinsic laser phase noise, gets averaged over this photon storage time tau, and hence, because frequency is simply a time derivative of phase, our frequency noise gets reduced by inheriting the stability from a stable phase over here. However, it's worth noting that this inheritance only applies for frequencies that are above the cavity pole. And it turns out that our science band actually lies significantly higher than that. So we needed a way to mitigate frequency noise at these higher frequencies. What we ended up doing was look at the transmitted light. And the reason is because the cavity acts as a low-pass filter, as shown by this dashed curve over here, which means that the product of the dashed curve with the orange curve then now gives you a blue curve over here. Hence, you don't suffer an increase in the frequency noise at these higher frequencies. And we did indeed, and after this reconfiguration, we did indeed observe a significant reduction in our noise floor by almost an order of magnitude. And once again, I'll state, just to give you a sense of scale, our science band, which is determined by the mechanical resonance frequencies of these rigid objects, which tends to be in the tens of kilohertz, is almost 2 orders of magnitude greater than the cavity pole of a kilohertz, which is why this technique is very powerful. I'll state that there's a bunch of other techniques that you can, there's a bunch of other solutions to this problem aside from the solution we implemented. We just implemented this solution because given the constraints of our project, this seemed like the path of least resistance. Since Urosh is in the audience, I'll offer some advertisement, is that he brought to my attention this very cool technique of using an optical fiber delay line to tackle this exact same problem, because the main problem was your cavity starts acting as a phase discriminator and not a frequency discriminator above the pole. But by its very nature, an optical fiber delay line is a frequency discriminator, and hence you can overcome this problem in a very elegant way. And it's something we will explore in future generations of this experiment. Okay, so that brings me to the end of the technical section where I walk you through all the different subcomponents. So here's a summary of what our apparatus looks like. Next, I want to talk about our first dark matter observing run. As a reminder, we're looking for the difference frequency at this photodetector over here, where we look for oscillations of these two nearby modes due to dark matter, whose frequency is the dark matter Compton frequency. What this corresponds to in the frequency domain is essentially a carrier corresponding to the RF spacing between the two modes, and these tiny sidebands which would correspond to the dark matter signal. So we're essentially looking for these sidebands when we look for dark matter. We don't care about this carrier, so we essentially eliminate it by passing the output of the photodetector through this RF delay line frequency discriminator, which is useful because due to its self-referential nature, it'll get rid of slow drifts in the carrier. We store the resultant data stream as a time series on a computer using a DAC card. Here's what that stream looks like, with the blue being our raw data. In the background, I have overlaid what a hypothetical dark matter signal would look like. Note the discrepancy in the scale, where the blue is in the kilohertz and the light orange is in hertz. So it's like we're really looking for a tiny signal buried inside our noise. However, I'm sure most of you know that time domain is not very useful, so we do an FFT of the whole data set, and we scan this entire spectrum to look for very narrow peaks that look something like this, given by the purple curve. The width of this feature is given by the coherence time, which I discussed in the physics section of the ultralight dark matter. And note there's a discrepancy of almost 6 orders of magnitude. The width is on the tens of millihertz, where our frequencies are in the kilohertz range, so we're really looking for a needle in a haystack. This particular shape comes from the Maxwell-Boltzmann distribution that you saw earlier. So combining both the shape and the width allows us to eliminate these other peaks as not being dark matter. If you really zoom in, you'll see that this peak is nothing but a local elevation of the noise floor, and hence we are able to rule those out. To do a much more rigorous search, what we do is that we take this the points in our blue spectrum in this frequency window. They're adequately modeled by white Gaussian noise, as shown over here. And when we do a fit, we extract the variances, and using those variances, we define a 95% confidence detection threshold, given by this orange curve. And since none of the points in blue lie above the orange curve, we conclude that there is no evidence of dark matter in this spectrum. However, as I said at the very, very beginning, even in the absence of a discovery, we can still set limits on the coupling of dark matter to ordinary matter, which is what we did. We used a technique, we took the exact same spectrum and used a technique known as Bayesian inference. So as a reminder, we are trying to set limits on this coupling constant in red, DME, and the strain that we measure in the lab is this optical strain, which is related to the dark matter strain through this detector response function, plus some noise term. Now, we're operating in a regime where the noise term overshadows the dark matter term precisely because we did not see any evidence of a feature like this in our spectrum. So, in this Bayesian inference method, we have to take the blue curve, the yellow curve, and the purple curve as input parameters. We plug it into a formula to come up with a probability distribution function of the parameter DME. And by integrating this curve to 95% and solving for this value over here denoted by this dashed line, we can say that we can rule out values of DME above this level with a 95% confidence level. So this is only for a given value, a fixed value of FDM that is parked at 50 kilohertz. We want to obtain a frequency-dependent limit on the coupling constant DME, so we step the frequency of dark matter and redo this analysis, and then generate a curve that looks something like this, where you have coupling constant as a function of dark matter Compton frequency FDM. Applying this technique to the two different models that we saw, in the standard halo model, this is what our exclusion plot looks like, where the shaded gray regions show you the region of the parameter space that was excluded in our first observing run. Note that compared to other experiments, we have an improvement by up to 2 orders of magnitude. Here's a zoom in of the red dash box, which is close to our science band. In the relaxion case, as a reminder, we have a 12 order of magnitude boost in the dark matter density, hence a 6 order of magnitude boost in the field amplitude, which is, so you would expect an equal 6 order of magnitude reduction in the limit that we set on our coupling constant, which is exactly what you see as given by this exclusion plot over here. Note that compared to the equivalence principle violation, which interprets phi as a fifth force mediator, does not benefit from this model because they're not interpreting their field phi as a dark matter candidate. Although it could be, it's relatively insensitive to the local dark matter density. So our limit has now exceeded, in addition to the other experiments that fall in the category of our experiment, have exceeded the equivalence principle violation bound over here. One caveat I'll point out is the fact that the field is stochastic, right? And this is important because very early experiments missed this point and set overly optimistic limits on DME. And we got around this problem by using Bayesian inference methods, which I discussed in the last couple of slides. And a consequence of using Bayesian inference methods to set limits on DME is the fact that our limit gets really bad at lower frequencies. That's because in the relaxion model, the coherence time is greater than our 4 days of measurement time. In fact, if you look at something in the 20-ish kilohertz range, the coherence time can be on the order of weeks. So that's why the limit suffers. Now, the Bayesian analysis is a bit of a black box and it's not very intuitive, which is why I didn't really put a lot of equations explaining how it works. But here's still a simple way to understand it. Here, let's revisit the time domain simulation that I showed you at the very beginning. Our dark matter field amplitude is oscillating like this because of its stochastic nature. If it turns out that we get unlucky and our 4 days of acquisition time happen to lie somewhere over here, then we will sample a much smaller amplitude. So we have to account, we can't use this formula because this is only valid when you've averaged over many coherence times. So the Bayesian inference method automatically accounts for this factor and leads to a reduction in sensitivity when your experiment is no longer above your coherence time. So with that, I'd like to summarize our two main results. We had two models. One was the standard halo model. The other one was the relaxion star-bound to the Earth. In both cases, we managed to exceed previous limits by up to 2 orders of magnitude. Before I get to my acknowledgement slide, I just wanted to advertise a potential upgrade to this experiment, which is instead of using 2 rigid cavities like shown over here, one thing you can do is you can do a LIGO hybrid, which is use a rigid cavity over here compared to a non-rigid cavity. In fact, we started out with this as our first experiment, but I'm sure you can imagine that vibration isolation is no walk in the park, and it took LIGO about 40 years to perfect this, and our project cycle was about on the order of like 3 to 4 years. So we in the middle we switched to this version due to the technical challenges associated with this. In fact, our cryostat vibration isolation is overkill for this system, in case any of you were wondering. It was originally built for this system, but hey, it still helps. So in the future, we can look forward to maybe implementing this version. The reason this is very attractive is because if you recall, the resonance frequencies of these rigid bodies tends to be like very high because they're very stiff in the tens of kilohertz. That limits the frequency window in which you can set limits on dark matter. However, these pendulums are very soft and they have a resonance frequency on the order of a hertz, which means now you can get access to these lower frequencies over here. And that's in contrast to the limit we already set in the solid red curve. All right, so with that potential upgrade on the horizon, I'd like to conclude the talk and thank our team at Northwestern, and a special thanks to these individuals for helpful discussions. Thank you for your attention. Mm-hmm.
Thank you so much.
Mm-hmm.
Do we have questions?
So two questions. Maybe the first one, so you said that basically at low frequencies you're limited by the coherence time.
Yeah.
How far could you go down in frequency, let's say if you measure for 4 months instead of 4 days or 4 years instead of?
Yeah, so the equation is it's the coherence time scales as 1 over f cubed. So in the standard halo model, it scales as 1 over f. So you're getting hit by a factor of f squared. So I'm not sure if I can do the math in my head, but it very non-linearly gets suppressed. So it's going to really blow up if it's a week at frequency, let's say 10 kilohertz. If I wanted to go to 1 kilohertz, that's, I don't know, like 100 weeks. Yeah. Yeah.
So when you showed the vibration isolation, I think you showed the transfer function for one stage very briefly, and it was like 3 orders of magnitude below 10 hertz.
Mm-hmm.
I guess that's the overkill because you don't need that right now. But you also said you have 3 stages. So does that mean that the total transfer function is actually like already 9 orders of magnitude at 10 hertz?
Yes, that's right. It's that would be what we would expect theoretically. If you want to verify that that is indeed the case, what you would have to do is that you would have to actually build a suspended cavity and actually measure how finely, because there are no accelerometers that are that sensitive. So, but at least in principle, yes, we have not verified that it actually multiplies very nicely. We only tested one stage because accelerometers work in that range. Yeah. Yeah.
So just on this vibration oscillation, do you have any idea what vibration the flexible strands carry? It's not zero, right?
It's not zero, no, but the hope is that when you have very bulky objects connected to like very flimsy links, in fact, I apologize for the units, but this is 4/1000 of an inch thick. So it's really just aluminum foil that's pulling on something that weighs a few kilograms. So theoretically, yes, it is transmitting vibrations, but hopefully not that much.
General question, what's the intuition behind the frequency range for that specific dark matter field?
The frequency range,
Dark matter frequencies of that you introduced in the beginning.
I think it's mostly, you mean like the 80 order magnitude plot that I showed at the beginning?
No, basically the microsecond scale, so tens or hundreds of kilohertz
Uh-huh.
frequency range.
Oh, that's mainly because we're limited by the the uh, the length of the cavity and the resonances over here because we lose sensitivity at much lower and higher frequencies. So you need to, in order to broaden your range.
You introduced the dark matter frequency in the beginning, right?
Yes.
That is on what scale for what you're looking at now?
Oh, that's gonna be what we're probing is a small fraction of that, which is all right. So this goes from 10 to the minus 22 to 10 to 1 eV. Ours, if I convert the from frequency to mass, is about 10 to the minus 13 to 10 to the minus 11 EV. Yes.
And as the frequency, you simply define
Yeah.
now h over the energy.
That's right. Yeah. The Compton frequency.
Okay. Good.
Yeah. The conversion factor is 4 times 10 to the minus 15.
Okay.
Yeah.
Other questions?
Yeah. Do you with the dark matter wind model, do you expect like seasonal variation?
We do, yes. What's going to happen is that you saw now, even though maybe that's not quite what you were asking, I'll mention this because it's off leads to a lot of confusion. Is the fact that we're looking for a scalar model, so there is no directionality to the dark matter itself. So people ask often that what if you oriented your cavities in an L shape as opposed to like parallel to each other? It doesn't care because it's isotropic. That's why it's a scalar model. However, the annual modulation that a lot of dark matter people talk about, what's going to happen is that the center is given by the galactic orbit speed, right? Now, the galactic orbits, this dash line is going to fluctuate left and right as you go through the year. Now, this number is like 10% of its value, so it's safe to ignore that when we set limits. But if we have a positive detection, we are expected to see something changing on an annual basis. Because when we set limits, what matters more is the area under the curve, which stays constant even if the profile itself is moving sideways.
Okay. Excellent.
Mm-hmm.
So, thanks a lot.
Mm-hmm. Thanks.